Okay, so
so last time we started studying Jordan canonical form. So the setup is V is a finite dimensional vector space over a field K, and E is a linear operator. And its characteristic polynomial fx is a product of linear factors. So x minus lambda 1 to the power k1, x minus lambda r to the power kr. And we know that from the theorem of symmetrical forms, D is isomorphic to is a module to what was it? Kx to the power and divided by some ideal which is generated by so it was actually like this v1 direct sum kx v2 direct sum kx v1. And since each vi divides the characteristic polynomial, so x vi x divides f of x, each vi is also a product of this factors, linear factors. And then we have seen the following. So kx divided by vix, and suppose that this vix is something like this. So suppose vix is just x minus lambda 1 to some power, let's say s1, s minus lambda r, x r. Geçen sefer bunları ne yazmıştım? Divided by the so lambda x minus lambda 1 to the power h1, x minus lambda r to the power r. We have seen that this thing is isomorphic to the following. Yani K'yı buna göre K'si K birine ayrı ayrı değil. Gayet son olmakla yanlış. So it is therefore enough to understand only one of them. So let's just consider one factor kx x minus lambda to the power of something like this. Okay. Burada tabii ki T'nin action'ı neydi? T'nin action'ı so here this is not to şöyle yapayım. Okay. So we have the following. We have vector space V, and here we have the action of T, and this is isomorphic to direct sum of such things, and so this is a factor of this x minus lambda r,
Bu isomorfizm değil, değil mi? Bu nesne, bu tip nesnelerin direct sum'ı. So this is an inclusion, injected map. Yani bunun içinde inside B, we have many copies of this kind of gadgets for different lambdas and different R's. So this is just one factor. And here, this operation on the vector space by T is transformed to multiplication by X. Değil mi? Burada bir vektöre T uygulamak, burada o vektörün karşılık geldiği polinomu X ile çarpmaya dönüştürüyor. Yani V, TB'ye gidiyor. Bu V vektörü, diyelim ki burada bir Px polinomu gidiyorsa, o Px polinomu X çarpı Px'e gidiyor. Değil mi? Böyle bir şey var. Burada P var, burada çarpı X'e. Peki, şimdi bu nesneyi Kx divided by x minus lambda power r has vector space, K vector space is structure with basis olarak da şunu alabiliriz. 1, x, bu r boyutlu bir polinom olduğuna göre r eksi 1'e kadar. Değil mi? Şimdi bu baz yerine şunu düşünelim. Instead, consider the basis. Yani burada v vektör uzayım var ama bu vektör uzayının içinde böyle bir parça var. Yani bu vektör uzayının bir direct temelli bu vektör uzayına izomorfik. Burada da t'nin işlemi x ile çarpmaya denk geliyor. Bu k vektör uzayı olarak bazı buydu. Ben bu baz yerine şu bazı düşünmek istiyorum. V0 birden olsun. 1 ile başlıyorum. V1 x minus lambda V2 x minus lambda squared and so on up to V r minus 1 x minus lambda to the power r minus 1. This is another basis. Okay? This is another basis. Bu vektör üzerine bakarsanız, değil mi? Sıfırdan r eksi 1'e kadar olan bütün polinomlar var. Burada da öyle. Yani shift edilmiş polinomlar ama buradan x üzeri r'yi çekebilirsiniz. Böyle yazmamızın nedeni şu. Let's see this action of Q on this part applied to this basis. So I would like to write down the matrix representation of this operator or this operator on this basis. Okay. So how would you get the matrix representation of an operator on a basis? You just apply your operator to each basis element and then write the answer in terms of the basis elements. So let's do that. Okay. So T applied to first basis element. Well, action of T is given by multiplication by X. So this is just V0 is just 1. So this is just X. Well, X in terms of this basis elements, how can we write this? Well, we can write this as what? V0, no. Lambda V0, değil mi? Bu lambda çarpı 1 artı x eksi lambda. Yani şöyle yazabilirim bunu. Lambda çarpı V0 artı V1. Tamam mı? Peki ikinci basis elemanı. So what is the second basis element? B1. What is this? This is x times x minus lambda. Well, this is just I can write it this way. So this is x minus lambda times x minus lambda. But then I have only x here. Here I have x minus lambda. So I should add just this digit, right? To get equality. And what is this? This is just lambda times x minus lambda, which is b1. So this is lambda times b1 plus x minus lambda squared. X minus lambda squared is just x minus lambda squared is just b. And then x minus b2, x minus lambda squared. So this will be just x minus lambda times x minus lambda squared plus lambda times x minus 2 squared. Well, what is this? This is just lambda times b2 plus b2. And so on. Okay, so finally we will have what? X times v r minus 2, v r minus 2. This will be again lambda times v r minus 2 plus v r minus 1. And the last one, x times v r minus 1. So this is just x times v r minus 1. This is x minus lambda to the power r minus 1, right? Okay, now what is this? This is just x minus lambda to the power r. Yani söyleyelim isterseniz x minus lambda to the power r minus 1 plus lambda times x minus lambda to the power r minus 1. But this thing is just x minus lambda to the power r plus lambda times x minus lambda to the power r minus 1. However, this thing is just 0. Why is that? Because that is the term we divide this polynomial ring, right? So this thing is 0. X minus lambda to the power r is 0 in this quotient vector space. Therefore, this thing is just 0. So this is just lambda times bn minus 1. So what is the matrix representation of this operator then? So, okay, right here. So, T acts on this widget some basis as nasıl ekleniyor? Şöyle ya da
Yes.
ne?
Yes.
Evet, yanlış. Şöyle. Okay, let me say. So, T has matrix representation on a summary of V
Ki o zaman şu, yani x divided by x minus lambda to the power r, let's say. D'nin bu tipte parçaları var. Burada x de çarpma olarak ekleniyor. Ama bu şu demek aslında, yani t'nin bir parçası var ve o parça üzerinde t'nin matris gösterimi şöyle. Nedir o? First vector, so V0 is mapped to lambda times V0 plus V1. So what is that? I will write this coefficients, right? I will write this coefficients lambda and 1. I have 1 here. As a column, my first column, lambda, 1, and then 0, 0, 0. And then the second vector is mapped to lambda times V1 and then 1 times V2. So it is this one, 0, lambda, 1, 0, 0. And then it will go like this. The one just before the last one. So r minus 2 is mapped to lambda times r minus 2 times 1 times r minus 1. So it goes like this. I have lambda here, and then here I have 1. Diagonalde birler var. Değil mi? Diagonalde birler var. And one picture. So here I have okay, 0, 0, 0, and I have this. So my operator has a matrix representation given like this on a suitable basis. Okay, this vector space has a basis so that on which T has this matrix representation. In general, what will be the matrix representation of T? Well, our vector space is isomorphic to, this gadget. And each of these gadgets is isomorphic to something like this. And these things also decompose like this. And each summand here is something like this, and that summand has on that summand T has such a matrix representation. Tamam mı? So for example, let's do some example. Say T is a linear transformation from E to B, and D has, let's say, dimension on K, let's say 10-dimensional vector space, and T has what? Invariant factors. Şöyle invariant faktörler olsun. D1 1 olsun. Şimdi 10 tane invariant faktör olacak. Şöyle bir ilk 5 tanesi 1 olsun. Tamam mı? Ondan sonra D6 şey olsun. X minus 2 X minus 3 olsun. 7 bunun böleceği bir şey olacak değil mi? X eksi bunun karesi x eksi 3 olsun. Ve şimdi bu üçüncü dereceden bu şey oldu. Yok. 5 oldu. Geriye 5 tane daha kaldı. Ama en azından bu olacak. O zaman şunu söyleyeyim ben, bu 7'ye kadar bir olsun. Bu 8 olsun. Bu 9 olsun. D10'da şöyle olsun. X eksi 2'nin kübü olsun. Şimdi bu ikinci dereceden 5, 8 oldu. Ve x eksi 3'ün karesi olsun. Tamam mı? Diyelim ki bu. Hepsinin çarpımı karakteristik polinomialdir. So f of x, the characteristic polynomial determinant of x minus identity minus t is the product of all these digits, and that is what? X minus 2 1 3 6 bu da x eksi 3'ün 4. Değil mi? Evet. So our matrix, this is equivalent to this gadget, right? And V1, V2, V3. It is like this. Tamam mı? Is this matrix or transformation diagonalizable? You can say it like
No, hocam.
Hmm?
No, hocam, because the minimal polynomial doesn't consist of the linear multiples of, I mean, these eigenvalues.
Yeah, it is not this is the minimum polynomial, right? This is the
Distinct values, hocam, sorry.
it is not the product of distinct linear factors, right? It has repeated linear factors. Therefore, it is not diagonalizing. So, T is not diagonalizable, but it has Jordan form because the characteristic polynomial or the minimum polynomial is a product of linear terms. If this was product of distinct linear terms, then it would be diagonalizable, but it is not. Now, what is the Jordan form? So what is the Jordan form? The Jordan form, Jordan canonical form of P on U, which is algebraic equation, is as follows. Şimdi T yani şunun üzerinde V vektör üzeri, so V vector space
is just isomorphic to kx divided by d1 up to kx divided by d10. d1 is 1, so 1 means 1 times kx, so right, this is d1. This ideal is the whole ideal. Therefore, we divide this vector space by itself, so it gets 0 there. So they are all zeros up to nereye kadar? Kx neydi bu? D8 x eksi 3 x eksi 2 x eksi 3 kx divided by x minus 2 squared x minus 2, and then the last one is kx divided by x minus 2 cubed x minus 2 squared. Okay, and each, of course, these things also breaks into pieces. So B is isomorphic to okay, now this thing will break into two parts. X divided by x minus 2, x divided by x minus 3, and then x divided by x minus 2 squared, x divided by x minus 3, and then x divided by x minus 2 cubed, and x divided by x minus 2 yanlış yazdım. X minus 3 değil mi şu? X minus 3 square. Okay. Now, so what is the matrix representation in some basis? It will be as follows. It's a 10 by 10 matrix, 10 by 10 matrix. This is dimension 1, dimension 1, 2, dimension 2, 4, 5, 6, 10, right? So it's a 10-dimensional vector space. Now, on this vector space, what is the matrix representation? So it is Jordan block. It's a Jordan block, but it's a 1 by 1 block. So it's a Jordan block, but size 1 by 1. So it is only this one. And the lambda there is just lambda is just 2. So I have just regular 2 here. And then what about this? It's a Jordan block, and it has dimension 1 again. So it's like this.
Hocam kamera.
Kamera, evet. So this one gives us a Jordan block like this. This one gives us a Jordan block like this. And then I have a Jordan block of size 2. So Jordan block of size 2, it will be like this. And the number is just 2. So I have this 2, 1, 0, 2. Okay. And then I have another so this one gives us a Jordan block of size 2, and then this one is a Jordan block of size 1. And it will continue like this. Another Jordan block of size 3. So here we have this kind of Jordan block. So 2, 0, 0, 1, 2, 0, 1. Okay, something like this. And then another Jordan block. And for this one, it will be just Jordan block of size 2. So this game. Efendim? Ha, şurası. Tamam. Sağ ol. Bir daha yazayım bunu. Let me write the matrix one more time. So, P in some basis. You may ask, what is this basis? How do you find this? Well, that is a different story. I didn't tell you how we can find this basis yet. Okay, it will be another story. We know that, I mean, we can just actually follow this isomorphism. Sorry. Here I say there is an isomorphism, but we didn't write down this isomorphism explicitly. This isomorphism consists of several things. How do you find this isomorphism? Well, we write down the characteristic matrix, and then we apply row and column operations. We find the symmetric normal form. You know, finding that thing consists of several actually operations. Each operation corresponds to an isomorphism, and at the end you have to take the composition of those isomorphisms. Okay, so you cannot just keep track of those isomorphisms. However, once we know that there is a basis in which our linear operator looks like this, we can go backward and find that basis, and I will tell you how to do that. Okay? Yani cevabın ne olacağını bildiğimiz zaman onu buluruz. Ve cevabın ne olacağını biliyoruz. Tamam mı? Okay, so let me rewrite one more time. So here I have 2, and then here we have 3, and then we had 2, 0, 1, 2, and then we had 3 by 3. Sanki şeyi atladın mı?
Hocam 3'ün de 2 olması gerekmiyor mu sol taraftaki? Yani sol taraftaki tahtada.
Evet, şunu unuttun değil mi? Şurada bir de şu var. Ha yok, unutmuşum. Burada var. Okay. Ondan sonra buraya 3'e 3 blok geliyor. 2, 0, 0, 1, 2, 0, 0, 1, 2. Tamam. Bir de en sonunda pardon, şöyle düzgün yapayım. Three, 0, 1, 3. And all other entries are 0. Okay? Tamam mı? Anlaşıldı mı? Okay.
Hocam yukarıdaki 2'nin çaprazındaki 3'ün 2 olması gerekmiyor mu?
Yok. Şurada 3 yok. So this is 3.
Tamam hocam, tamamdır.
Yazım kötü olduğu için. Okay. Peki. Şimdi bir tane de örnek yapalım.
Can I ask you a question?
Yes.
Would you give the definition of the Jordan canonical forms? What blocks means? Their formal definition?
So what's the Jordan canonical form? So what we have seen so far that if our characteristic polynomial is a product of linear factors, then there is a basis, and on that basis, T has a matrix representation consisting of blocks like this. We call them Jordan blocks, let's say R of them. And each of these is a block consisting of entries like this. On the diagonal, we have suppose this Jordan blocks corresponds to some eigenvalue lambda. We have lambda on the diagonal. Above the diagonal is 0, and below the diagonal I have ones. So this is the Jordan block, and T has a matrix representation like this, where each of these is a Jordan block of appropriate sizes. Of course, I mean, we can shuffle these gadgets because, so it depends how you construct your bases. I find basis first for one block, and then I find another basis for the second block, and so on. If you just shuffle those basis elements, then you will get a completely different representation. You can interchange these blocks.
Özellikle son verince x eksi 2'nin küpü çarpı x eksi 3'ün karesi. Biz onları yine istediğimiz.
Tabii. That just corresponds to changing orders of elements in a basis. And if you do that, the matrix representation will be changed. Okay? So, Jordan canonical form is unique up to permutation of this, Jordan blocks. And a Jordan block is this gadget, a Jordan block. Okay, understood? Now, what's a Jordan block? And
Okay, thank you.
This matrix representation is not unique, of course, because you can just, shuffle the vectors, and these blocks can interchange. But up to, permutation of these blocks, it is unique. Okay. Now, let me do one example. A concrete example where we find this Jordan blocks explicitly writing down bases and so on. Okay. Okay. Ben öyle örnek yaptım. Ben nereye koydum? Burada. So it's a 5 by 5 matrix. Of course, you can get something bigger size, but it's not easy to make the computation. So but using the online calculators, you can build your own examples. Okay. So consider the linear map, linear operator from, let's say, R5 to R5. So let me work with real numbers. Given in some basis by the matrix representation. Representation. T. So in some basis, let's say this is given by this matrix representation. -1, 0, 2, 0. -9, -1, 0, 6, 0. 0, -1, 2, 1, 0. -10, -10, and then -4, 0, 7, and 1, and then -22, -8, -8, 0, 13, and 3. Don't ask me how I found this. I had actually started with something else, but then it just evolved into this gadget. Okay. Now, so let's say the question is the following. Find its canonical form. I should say Jordan canonical form. Because diagonal form is just a special case of Jordan canonical form, right? If you have just blocks, 1 by 1 blocks, then it's a diagonal matrix. Well, how can we do this? Well, we have to write down the matrix Px minus x times identity minus t, and then apply row and column operations to this matrix and find the symmetric normal form for this matrix of polynomials. And I will not do that, but suppose we have done that, and let me tell you what the okay. Şey şu, nerede o? Şöyle. Okay. 1, 1, 1, and then x minus 2 squared and x minus 2 cubed. So these are our invariant factors. Invariant factors. So our invariant factors are what? So the invariant factors are P1, P2, P3 are just 1. P4 is x minus 2 squared, and P5 is just x minus 2 to the power 3. So I have only one eigenvalue, which is just 2. What is the characteristic polynomial? That is just the product of these. So it is x minus 2 to the power 5. Okay. The minimum polynomial, D5, x minus 2 cubed is the minimum polynomial. in particular, our matrix is not diagonalizable. And what is the Jordan canonical form? Well, we have only one eigenvalue, and this gives us a 2 by 2 block, Jordan block, and this gives a 3 by 3 Jordan block. So we have a block of size 2 and size 3, and that's it, right? They in total give us a 5 by 5 matrix. So there is some basis, and on that basis, our linear map has a matrix representation like this. Zero, 1, 2, 0. Okay. But the question is, how can I find that basis, right? So, en altta da 2. Yok, burada var. Burada bir 3'lük blok var. So I have a 3 by 3 block and a 2 by 2. Tamam mı? So how can we find this basis? So here we will do, I guess, kind of inverse engineering, right? We know what the result is. We have to just go backwards and try to obtain a basis which gives us this matrix representation. Okay. I will not, give the algorithm in general, because, if I do that, it will look so complicated. It will be something theoretical junk, and it won't be useful. Instead, I will explain you how to find this basis on this example. Once you understand, one example clearly, then the rest is easy. That's not a theorem or anything. That's just an algorithm which tells you how you proceed to obtain the spaces. Of course, you use your theoretical knowledge, but I mean, okay. Şöyle diyeyim. Now, this is the minimum polynomial. Therefore, the operator t minus 2 times identity cubed, right? So this is the operator which corresponds to this polynomial. This is 0 on V, right? Because this is the minimum polynomial. So this operator is 0. Now, note that since V5 is x minus 2 cubed is the minimum polynomial, P minus 2 times identity cubed is equal to 0 on the vector space. Peki, şimdi let's look at this figure again. Once we proceed, okay, now I have two eigenvectors, right? Note that this column
corresponds to an eigenvector. And this column corresponds to eigenvector. Why is that? Because whatever the basis element, so this corresponds to the second basis element. And when you apply your operator to the second basis element, what you get? You get 2 times your second basis element, and that's it. Therefore, your second basis element is an eigenvector. And also, the last basis element is also an eigenvector because your operator applied to the last basis element is just 2 times 2 times the fifth basis element. So if these are the, let's say, basis elements, okay, then the second one and the fifth one are eigenvectors. What about these digits? Well, that's not an eigenvector because t applied to v1 is just 2 times v1 plus v2, right? T times v3 is just 2 times v3 plus v4. So the others are not basis elements. They are not eigenvectors. So here beta, let's say, and we know that note that B2 and B5 are eigenvectors. The others are not eigenvectors. And let me tell you what they are in the second hour. Let's give a break.